Hello everyone. Today I'm going to present the Annotate bench, which is a benchmark built around a practical question when label data is limited and how should we spend annotation budgets. In particular, which example should we label and how many labels do we actually need and when does further labeling stop being worthwhile. Before training a classifier, a team with a fixed budget already faced three decisions. The first is the example selection. Which items from the unlabeled pool should receive labels? And the second is the stopping point. Should we click 100 labels, 500, or 1000? And the third is the annotation source. Should the labels come from humans and LLM or a combination of both? These choices affect cost as well as model quality, but a single final accuracy score cannot tell us whether we selected the right examples or pay for more labels than we needed. That's the decision problem that Annotate Bench is designed to study. Our central research question is under a fixed annotation budget, which strategies produce the strongest downstream model? We answer it using three connected views. First, learning curves show how quickly each strategy improves as the budget grows. Downstream micro F1 tell us whether the resulting labels are useful for training a classifier, and cost performance frontiers show which combinations provide the best value. My contribution is not a new active learning algorithm. Instead, I built a reproducible benchmark pipeline that compares four selection strategy across 10 datasets and five annotation budgets. Under one control evaluation protocol, it produces learning curves, cost performance, frontiers, and an LLM labeling extension. This allows us to compare annotation choice fairly and connect them to a practical budget decisions. To make that comparison more meaningful, we need to keep the rest of the pipeline control. These slides show that control design. Across 10 public text classification datasets, we compare four selection strategy and five labeling budgets. In each condition, a strategy selects example from an unlabeled pool. We review the goal labels, train the same TF-IDF and logistic regression classifier, and evaluate macro F1 together with estimate costs. We repeated this across multiple seeds and cost scenarios, producing 3,000 measure result rows. The ultimate extension changes only one step. Instead of revealing goal labels, GPT-4o Mini generates the labels. The downstream classifier remains the same. That let us connect performance differences to the annotation strategy, budget, or label source, not a different training pipeline. So under this control comparison, does one selection strategy consistently win? The answer is no. Um, no strategy wins universally. Hyperactive learning ranks first on 5 of the 10 datasets, so it has the largest number of wins. But random sampling and uncertain sampling each win on two datasets, while the diversity sampling wins on only one. However, the winner changes with the dataset and budgets. In several cases, the top confidence interval also overlap, so a small ranking difference may not be reliable. Random sampling therefore remains an important baseline. Greater complexity does not guarantee more useful training data. The identity of the winner is only one part of the decision. We also need to know how much data is enough. So, um, financial phrase bank illustrate the second question. At small budgets, the strategy behave quite differently. As the numbers of labor grows, uncertain sampling improves substantially. At 500 labels, it reaches a macro F1 of 0.755. What matters here is the shape of the curve after the point. Moving from 500 to 1000 labels creates almost no additional improvement for the leading strategy in this setup. If we reported only the result at 1000 labels, we should miss the useful decision. Nearly the same performance was already available at half that labeling budget. So learning curves do more than rank strategy. They review where the value of additional annotation begins to flatten. The next step is to express that decision in the unit organization usually care about, which is the cost. Here, each point represents a strategy and budget combination. The vertical axis shows the macro F1 and the horizontal axis shows the estimate direct cost. The black line here is the parallel frontier, the options for which nothing else is both cheaper and better. This separates two decisions that are often mixed together. The highest point gives the best performance, and the frontier show which choice are efficient at different spending levels. The outend points appears further left because the direct API cost is lower, but this excludes human review, retries, latency, and quality control. So, cost therefore help us compare annotation choices, but cost alone does not tell us whether the generated labels are useful. This brings us to the LM extension. In these figures, the horizontal axis show the agreement with goal labels, and the vertical axis show the downstream F1 gap from the best goal label strategy at the same budget. If accuracy determined downstream utility, high agreement datasets would all sit near the zero line, but they do not. For the yaw polarity, the agreement is 0.972, and the downstream model almost matches the best goal label results. The financial freeze bank also has a high agreement at 0.929, but its downstream model still trails by 0.045 micro 1. And the AG news shows an even larger downstream gap. So we must ask not only how many labels are correct, but where the error occurs and what models learn from them. An LM annotator should therefore be evaluated as a complete annotation strategy, not only through label agreements. So far, the benchmark has used TF-IDF with logistic regression to keep the comparison control. We then repeat the evaluation with sentence transformer embeddings. Performance improved on 8 of the 10 datasets, with particularly large gains on 20 newsgroup, emotion, and tweet eval sentiments. However, the change is not uniformly positive. As we can see, the yaw polarity changed very little and the track performs worse. These robustness checks show that annotation strategy and downstream representation cannot be treated as completely separate decision. An example selection method is useful only in relation to the model that will learn from the selected data. Taken together, the results suggest three practical recommendations. First, do not choose an annotation strategy by default. Compare learning curves on the target datasets and the budget that actually matters. And the second, stop at an efficient point when further improvement no longer justifies additional cost. And the third one is evaluate LLM labels downstream together with their error patterns and the real cost of quality control. The benchmark also have some limits. It focuses on text classification and simulates annotation by revealing goal labels, so it does not capture human disagreement, fatigue, and ambiguous instruction or interface effects. They're not just caveats, they define the next stage of the research, measure human workflows, supported task types, and more complete evaluation of LLM assisted annotation. So to conclude, Annotate's bench treats annotation as a decision that should be tested empirically. There is no universally best selection strategy, and learning curves helps identify when to stop. and how label accuracy does not necessarily produce an equally strong downstream model. So the main message of this research is do not benchmark annotation in the abstract, benchmark the decision you actually need to make. Thank you. I'm happy to take any question.